Hello everyone, my name is Boibhav Chatterjee and I am a fourth year PhD student at Purdue University, working with Professor Shreyas Sen. It is a great pleasure for me to be able to present our work on a sub 25 microwatt phase lock loop or PLL for IoT and body area network applications with 1 to 450 MHz frequency tuning and multi-phase outputs to be used in conjunction with CDRs in traditional wireless architectures. We'll start this talk with the introduction and motivation for an extremely low power PLL, followed by the circuit level and system level design space explorations for the voltage controlled oscillator and the full PLL system respectively. We'll then present our simulation results and compare them with the state-of-the-art PLLs in literature with large tunability. Finally, we'll conclude this talk by summarizing our contributions. Now, today's Internet of Things, or IoT as we know it, is at the juncture of Moore's law and Shannon's law. Moore's law, up until today, has been enabling cheaper and cheaper computation on smaller form factors through technology scaling, while Shannon's law has continued to increase the channel capacity by supporting high bandwidth communication links. And these two laws together are the keys to enable ever more efficient future systems. But there is a cost of having more computations or supporting larger channel bandwidths, and that comes in the form of power consumption. Therefore, one of the major challenges in designing IoT systems has always been the energy efficiency. And naturally, the question arises, how to reduce the energy consumption in the system? If we look at the energy efficiencies of computation, communication, and clocking, which most of the times is implemented with help of a PLL, we see that the energy for computation is orders of magnitude lower than the energy for communication and clocking. Recent designs have already seen a strong push towards sub 10 picojoule per bit communication, especially for body area network and implantable applications. However, there is not much work that has been put into achieving extremely low power clocking, and this is what we address in this paper. Now, looking at a traditional PLL architecture, we first have a phase frequency detector or PFD, followed by a charge pump, a loop filter, and a VCO. A reconfigurable divide by N circuit enables tunable frequency generation at the output of the VCO, as the output of the divide by N circuit closely follows the reference frequency through the negative feedback in the loop. Generally, the VCO is the major source of power consumption, followed by the divide by N circuitry, the PFD, and the charge pump. Hence, our first target is to investigate and reduce the power consumption in the VCO, as we shall see in the subsequent slides. Till now, we have talked about clocking applications in IoT systems in general. Let's take a look at a special scenario of a low-power wireless body area network or WBAN. The United States National Health Expenditures Report shows that the total expenditure on healthcare was $3.6 trillion in 2018, which is projected to increase to $5.1 trillion by 2022, almost 20% of which would be on personal healthcare devices. This growing market has led to increased research efforts to make these systems low cost, low power, or even batteryless. And having an extremely low energy clock will make them even more efficient. The data rates required for personal physiological monitoring are generally in the range of a few kbps to tens of mbps for multi-channel recording scenarios. The energy for communicating the data bits is in the range of 10 picojoule per bit to about a nanojoule per bit, as shown in the plot on the top right. The x-axis shows the data rates and the y-axis represents energy per bit. One of our earlier works show that it is even possible to achieve sub 10 picojoule per bit energy efficiencies during communication. Hence, in this work, we have targeted a PLL energy consumption which is at least 1/10th of the communication energy, that is less than 0.5 picojoule per cycle. To support the wide range of data rates from a few kbps to tens of mbps, the PLL frequency is chosen to be within a megahertz to about 500 megahertz. Additionally, it must be noted that for wireless transceiver applications, there is a multi-phase clock requirement for the CDR, or the clock and data recovery circuit, and hence the PLL should be able to generate multiple phases of the clock. Looking into further details of the multi-phase requirement, there are three distinct choices that the designer can have. First, we can have a PLL with a single phase output, which would be followed by a phase interpolator or PI to generate multiple phases for the CDR. However, PIs are usually employed in high frequency GBPS links as their designs are more suited to applications where the individual gate delays are a significant portion of the cycle time. Hence, PI design at low frequencies within 1 to 500 MHz becomes a challenge. The second choice would be injection locking a multi-phase VCO to generate multiple phases of a fixed reference frequency. However, frequency tuning becomes an issue in this scenario. Additionally, single-phase injections lead to significant phase asymmetry among VCO outputs, which is why controlled multi-phase injection becomes necessary. The third approach would be to have a PLL with a multi-phase VCO, for example, a ring oscillator-based VCO. This is the focus of the current work, and we address the low power requirement of such a topology. With this, we shall look into the design space exploration of the VCO architectures available to employ in a multi-phase PLL. The first architecture that will be explored is a supply regulated VCO, or SR VCO, wherein the supply voltage of the ring oscillator-based VCO is modified to generate tunable frequencies. This is achieved through an LDO where the reference voltage of the LDO is provided by the PLL loop as a control voltage. Please note that in this case, the LDO is part of the PLL, which leads to important system-level considerations as we shall see later. The second architecture is called current-starved VCO, or CS-VCO, where a control voltage is used to starve the current in the ring oscillator to tune the frequency. This control voltage comes from the PLL as an output of the loop filter, while the supply of the ring oscillator is decoupled from the PLL, which means that the LDO reference can be provided separately to have a second mode of control on the VCO frequency. The third topology will be called VCO with controllable RC delay, or RC VCO. In this architecture, individual RC delay blocks are connected to the output of each stage of the ring oscillator. The resistor is implemented with a MOSFET in triode, for which the control voltage is supplied from the PLL that controls the overall RC delay. The capacitor is implemented with a standard MOS cap. Please note that just like the CS-VCO, in RC-VCO architecture, the supply of the ring oscillator is decoupled from the PLL, which means that the LDO reference can again be provided separately to have a second mode of control on the VCO frequency. Next, we compare the current efficiencies of these three architectures, where current efficiency is defined as the ratio of the oscillator's frequency to its current consumption. The 3D surface plots in bottom show the current consumption, achievable frequency, and F/I ratios for the three VCO architectures as a function of both the supply voltage and the control voltage. For SR VCO, the supply voltage is same as the control voltage, and hence we get a symmetric surface with respect to VDD and V control shown in blue. The RC VCO, shown in red, follows the blue SR VCO surfaces closely for higher VDDs and higher V controls. However, for a low VDD and low V control, RC VCO frequency reduces more due to additional RC delays. And hence, the F/I ratio becomes worse for the RC VCO. CS VCO, on the other hand, always requires higher currents to reach the same frequency as SR VCO and RC VCO due to additional transistors. And hence, the F/I ratio is always worse. Comparing the phase noise of these three topologies at 1 MHz offset for 300 MHz output frequency, we again see that the SR VCO and RC VCO closely follow each other, with the CS VCO being significantly worse than the two. Numerically, the SR VCO achieves an F/I ratio of 38 MHz per microampere at 300 MHz, while RC VCO achieves 29 MHz per microampere and CS VCO achieves only 10 MHz per microampere. Both SR VCO and RC VCOs can be designed within 15 microwatt for 400 MHz operation. This indicates that the SR VCO performs best both in terms of phase noise and current efficiency. However, it must be noted that the SR VCO requires that the LDO be a part of the loop, which has serious system level implications, and this is what we'll discuss next. If we use the SR VCO, the LDO reference voltage needs to be controlled through the PLL, as shown in this figure. Note that as the frequency of the VCO is varied, the bandwidth of the loop filter and the bandwidth of the error amplifier in the LDO also needs to be reconfigured. This is achieved through two controllable voltages, VB1 and VB2. Now, as we recall from the fundamental theory of PLLs, the VCO introduces one pole in the PLL, while the loop filter introduces 2 poles and 1 zero. For stability, one of the poles from the loop filter is designed at a higher frequency, so that there is a positive phase margin at the gain crossover frequency. However, we must note that there are 2 additional poles in the system, P4 at the output of the error amplifier and P5 at the output of the LDO. For stability, both of these poles need to be at a much higher frequency than the gain crossover point, which leads to 2 issues. First, the error amplifier requires a high bandwidth and hence consumes higher power. For the current design, the loop bandwidth varies between 20 kHz to 10 MHz as the PLL operates within 1 MHz to 500 MHz, which means that the error amplifier's pole needs to be at 100 MHz or more, leading to a power consumption of about 40 microwatt, while the VCO itself had a power consumption of only about 15 microwatt. The second issue arises due to the LDO's pole P5, which needs to be at an even higher frequency, and that means that the power supply noise rejection or PSNR will be bad for the LDO. Conversely, if P5 is kept at about 200 MHz and P4 further away from it, the power consumption of the error amplifier becomes even worse. To solve these system level issues, let's take a look at the RC-VCO based PLL. Please note that the current efficiency and the phase noise of the RC-VCO was almost as good as that of the SR-VCO. Moreover, RC-VCO enables decoupling the LDO loop from the PLL, as shown in the figure. The PLL controls the RC delay, while a separate LDO reference voltage, VB3, enables coarse control of the VCO frequency. Even in this architecture, there will be 1 pole from the VCO and 2 poles and 1 zero from the loop filter. And the placement of these poles and zeros will be same as the previous architecture. However, since the LDO is not a part of the PLL, poles P4 and P5 are now independent of P1, P2, and P3. As long as P4 and P5 are away from each other, the LDO loop will be stable. However, both of them can now be at a low frequency, leading to relaxed power consumption at the error amplifier, which becomes only 0.5 microwatt instead of the 40 microwatt in the SR-VCO based architecture. Furthermore, the LDO output can now have a large amount of decoupling capacitors due to the relaxed P5, leading to a better PSNR performance. With this, we'll look at some of the simulation results of the RC-VCO based PLL. All the simulations have been performed in TSMC 65 nanometer CMOS technology with 1 volt supply. This slide shows the transients of the PLL, wherein the time is represented in the x-axis and the frequency is represented in the y-axis for a 300 MHz output. At 600 microseconds, the frequency error becomes only 19.71 kHz, which is equivalent to only 66 ppm and can be tolerated by any traditional CDR. The timing jitter is observed to be 3420 ppm or 11.4 picoseconds, with a 200 millivolt peak-to-peak supply noise. The total power consumption at 300 MHz is only 21.12 microwatt, with 13.17 microwatt still being consumed in the VCO and 5.92 microwatt in the divide by N circuit. On the right hand side, we have plotted the energy per cycle of the simulated PLL with respect to the frequency of operation and compared them with other state-of-the-art tunable PLLs. At around 100 MHz, the improvement with respect to state-of-the-art is about 33x, with an energy consumption of only 70 femtojoule per cycle. Comparing the proposed PLL with available literature, we see that the 1 MHz to 450 MHz operating frequency leads to 450x tunability, whereas other works demonstrated a tunability between 1.5x to 64x. The power consumption is less than 25 microwatt, leading to best energy efficiencies and competitive jitter power trade-off FOM. However, it must be noted that ours is a simulated work while other works are measured. We shall implement and measure the performance of the PLL as a future work. In conclusion, we found out that the VCOs and LDOs are the 2 most power-hungry components in a PLL, and perform detailed circuit and system level architecture exploration to determine the applicability of the correct VCO topology for minimum system level power consumption. A wide tunability is demonstrated through split-tuned control, and best reported energy efficiency numbers are shown through system level simulation. With this, I thank you for your kind attention, and I am happy to take questions now. Thank you.